going to show you how to take the cat on the left and turn it into the cat on the right. And if you're thinking that nothing's going on there, that it looks the same, yeah, it does. There's absolutely nothing happening. It's a nothing filter. Let's go look at the source code in a little bit more detail than what we did in the YouTube short. So first of all, we have a function here. Function, F for function. IMG 2024 is the name of the library, so sometimes I like to name my libraries based on the year it was established, and so this is going to be established in 2024, because we only have a few more days before 2024, so I'm just rounding to 2024. Filter number 1, and filter number 1 does nothing. VOD here stands for void, it's a macro for void. Okay, so what do we have here? Every single function in our filter function library is going to take exactly 3 parameters, always in this order, so that we can create some type of polymorphism, some type of inheritance within our system, so we can create arrays of filters and apply different filters by just selecting different numbers eventually in some type of batch processing system. So gen pointer right here stands for general arguments, and it is also a macro to a more complex type name that's way too many fucking letters. And I is for input, right? So I underscore here, that stands for input. We have the general arguments. The nil is OK arguments. So these are the specific arguments for the function. And then we have the type of the function. So how do these work? Why are we taking exactly 3 arguments? Okay, so first of all, let's go figure out where gen is being defined, right? So let's go copy that for a second. Let's go up to the top of the file, and let's go Control F and look for gen. Let's go match whole word only. Let's go match case. Let's not wrap around, and let's go find next. Oh, so we see it right there. Gen. What is gen? Gen is this type that says type image 2024, and then it is 0 general. Okay. That's a lot of fucking words, and it's a struct, right? Then we have this other thing called any right here, which is to a struct which is of any kind. So these are kind of like the 2 most important types that the filter library is going to use. Why don't we go look at both of these? Let's go look at the general one right here. Let's go find the definition further down in the file. So let's go looking down. Okay, so struct image 2024 0 general. What is this? So first of all, the first 2 member variables of every single struct are going to be 2 unsigned 32-bit integers. The first one is going to tell you what the type of the struct is. So member variable type 0 general. And this 0 doesn't really belong, and I need to refactor it out because I decided to use the numbering system for the specific filter function arguments and not have a numbering system for the general filter function arguments. All filter functions will take this struct as its first parameter, right? So this variable right here tells us what the type of the struct is, some type of enumeration to tell us what it is. I do want this to be set to 0 always, so maybe keeping this 0 here is okay. This member variable, we are going to use this member variable to know whether or not the struct is initialized, because this is C code. We don't have the whole like array thing of like resource acquisition as initialization. So by having an initialization flag like this, if we 0 initialize the struct when we create it, this will be set to 0, and that'll tell us that the struct hasn't been initialized yet. Okay, so we have these 3 member variables for a pixel array. So member variable pix for pixel array, it is an array of unsigned 8-bit integers, 8 bits per byte. And so we have a pointer to unsigned 8-bit integer. This is my own macro that just points to the uint8 type from the stdint library. And then we have a signed integer right here, int32, the width and height. And also this is unsigned 32-bit integer, if I didn't already go over that. Okay, so you have the actual raw pixel array. You got the width and the height of the pixel array in pixels. And then we have this weirdness here. Now, why do we have this weirdness here? Well, I was thinking about it, and I think that every single filter should have settings for where you actually want to apply that filter. Now, we could get really complicated and do like weird ass polygonal selections or whatnot. But for my use case, a rectilinear selection makes the most sense. So we have 4 member variables for the left, right, top, and bottom inclusive edges of our selection region. Now, you might be wondering, why are these names so weird? Well, I don't know, because I'm fucking OCD. Okay, but besides that, what did these actually mean, right? Well, X is obviously for X-axis, Y is for Y-axis, right? And then 0 is for minimum, and 1 is for maximum, right? 0 is for minimum, 1 is for maximum. So if you are familiar with a little bit of linear algebra, sometimes in, I believe, what it's called, like a parametric function, you go from T0 to T1. So this is kind of like that, T0 to T1, but X's, right? T0 to T1, but Y's. And then we have L for left edge, R for right edge, T for top edge, B for bottom edge. So why do we have these letters here if we already have the 0s and 1s and the X's, right? Well, it's for redundancy, right? Obviously, this is very terse, and this is just a little redundancy to make sure that I know what the fuck I'm talking about, right? X0 stands for X minimum, which would be the left, right? X1 stands for X maximum, which would be the right edge, right? Y0 stands for Y minimum, which would be the top edge, because we have a top left graphical origin, right? Y1, that would be the maximum, 1 is for maximum, and B is for the bottom edge, right? So there are certain combinations of X's and Y's and L's and R's and T's and B's that would be completely invalid, right? So that's the reason. Okay, so obviously this is kind of crazy, and this is our general argument struct that gets passed into any filter function. All filter functions take this as their first argument. Okay, so let's go find the any kind, right? The any kind, which has a macro that's just called any in all capital. So whenever you see any in all capital, it's this struct right here. Whenever you see gen, G-E-N in all capital, it is this struct here. So what is any kind right here? Well, this is how we pull off polymorphism in C code, or how we pull off inheritance in C code. Every single specific settings object, and actually the general settings objects as well, all of these different structs in our code base have the same first 2 member variables. A uint32 telling us what type of struct we have, a uint32 telling us whether or not the struct is initialized. So m underscore is for member variable. All member variables of all structs in my code base will start with the m underscore. typ for type, ini for initialized, and then u32 for unsigned 32-bit integer. So why do we have this struct right here? Well, this struct allows us to have a little bit of type safety rather than just throw around completely void pointers. So, for example, if I have 2 different setting structs, and I want to and I don't know which setting struct I'm going to get, I don't have to cast that setting struct to a void pointer. I can cast that setting struct to this. And then I can look at the type flag to figure out exactly what setting struct it actually is, right? So that's one way to kind of pull off inheritance and polymorphism in C. Okay, so there's one more really important struct for the do-nothing filter, which is the actual settings filter, the specific settings for the do-nothing filter. Now, the do-nothing filter does absolutely nothing. So we see that this just says struct T image 2024, it is the settings object for filter number 1, which is the do nothing filter, right? So this is a type, a settings type for filter number 1, the do nothing filter. And all it has is member variables for type and are we initialized, and then instead of just calling it m type and m ini, we're adding a little bit more uniqueness to the identifier, right? It's for filter number 1, and filter number 1 does nothing. Now, if you're looking at this, you might think that maybe I should have done some composition, right? Like, another way we could have done this is instead of always including these 2 first member variables of every single one of these configuration structs, we could have just taken this, right here, and we could have made it the first member variable of this struct right here, right? So instead of using this, we could have just used that struct, right? So the address of the first member variable of a struct is identical to the base address of the struct. So the base address of a struct, the base address of the struct, and the address of the first member variable of the struct, those addresses are always the same exact address. And that's one of the key pieces of information you need to know in order to be able to like successfully pull off like inheritance and polymorphism in C. Okay, so this struct doesn't really have any configuration, right? It just has a variable that tells us what type of struct it is. So this value should be set to 1 when this object gets initialized, and this value should be set to a non-zero value once we have initialized the value here, right? Okay, so now that we've gone over that, why don't we go find that function again, right? So let's go Control F and go F image 2020, 2024. Oh boy, it's not 2020 anymore. So function image 2024. And then we know it is filter number 1, and filter number 1 is the nothing filter. So if I'm consistent enough with the way I do things, we'll be able to find it. And indeed, we found it right here. So it is a void function, so this is just a macro for void. It's a function f. It belongs to the image 2024 library, image 2024. It is filter number 1, and it does nothing. So now let's look at all these parameters here, right? So gen is a macro for the general settings that tells us the memory address of the actual pixel array and where we want to apply the filter to, right? Because we don't have to apply the filter to the entire pixel array. We can apply it to a subsection, and that sub-rectangle is included in these general settings. Now, the specific settings pointer right here, for every single one of our filter functions, it's actually a different struct, right? So we have this type is always the same, this type always differs, and this type is always the same, right? So if we look at another one of these functions, right? If we look at the inverter filter, it also takes the general arguments, but now it takes argument type 2, which is the arguments for the inverter function, and then it takes a uint32, right? And then if we go down here, we have a example function that doesn't do anything yet because we're not that far ahead yet. So filter number 3 is unknown. We'll refactor this with a name of whatever it does when we get to it. And it takes general arguments. It takes arguments, specific arguments 3, and then it takes a uint32. Okay, so why are we kind of like passing in 3 arguments like this? Why are we doing this? Okay, so the first thing is obvious, right? There are certain settings that are common to every single function, right? So if we want to apply the same filter to the same bitmap, if we want to apply different filters to the same bitmap, all of those filter function calls would use the exact same general arguments reference, right? So that's why the general arguments are always included. Now, obviously, different filters have different kind of knobs and dials and things that need to be twisted and turned. And that is why the second parameter is the specific arguments. Okay, but now the catch is, okay, well, this makes sense, but then what the hell is going on here with a third argument that if it's filter number 1, this has to be a 1 or a 0, right? If it's filter number 2, this parameter right here has to be a 2 or a 0. If it's filter number 3, this parameter here has to be a 3 or a 0. What the fuck is up with that? Why am I doing that? Okay, well, let's look at this. Sometimes we just want to call a filter and we don't want to have to fucking configure it, right? We don't want to be like, oh my god, all these knobs and dials. No, I just want to run whatever the default configuration is. I don't want to have to think about this part. Well, how are we going to call this function and not have to think about that? Well, what we do is we supply null, right? We supply null to this. Okay, well, if we supplied null to it, then how does it know the configuration object? How does it get a configuration object? Well, we could have just done this, we could have just done these two arguments, and then inside the function, if it detects that this is null, it could just look up the default configuration object for filter number 1, and then use that. That would be one way to do it. Here's the thing, though. I am not a Java programmer, and I think it's a horrible, horrible, horrible idea to just pass in null without any type of safeguard, right? So when I pass in null, I want to declare that it is null. And if I don't pass in null, I want to declare that, well, it's non-null. So this right here is going to help make sure that we don't make a mistake when we're passing in this object reference. When this object reference is non-null, then this value is going to be 0, saying that we do not have any type override. Type override being the override for the default configuration for whatever this object is. Now, when this object is null, then this value right here needs to be a positive value that is equal to the number in the shader function. And what that's going to allow us to do is look up a default configuration object that is of this type by going into a lookup table with this index here to fetch out the correct type. Okay, so let's look at what we have here. So we have some boilerplate, like all these lines that are marked with boilerplate right here. Every one of these lines is boilerplate. Now, what we could do with all this boilerplate is we could do some macro magic, and we could take all this, cut and paste it, put it into an include file, and just hide it away, right? Hide it away so we don't have to fucking look at it, because it's kind of scary, right? This boilerplate here and here is fucking scary to think that the whole function logic is actually only here, but yet we have all this boilerplate. We're not going to do that, though, because unfortunately, there's not really such a thing as a zero-cost abstraction. Okay, so we could definitely zero-cost abstract this into like a zero runtime cost if we took all this and just threw it into an include file and condensed this all down into one line. But that leads to a lot of file management problems, and it also makes the code harder to understand because now you got to open up another file to remember what all these macros are, or you see all these different variables and you're like, where the fuck did those variable declarations come from? Oh, they must be in that include file. Oh, great, now I got to open up that include file. So let's just go look at this. So what are we doing here? Like, why does this general argument that takes the general argument, why is this an argument object of type 1 that takes an argument object of type 1? What are we doing here? Well, first of all, remember that this can be null, right? So that means that what this function does is it takes the object reference to the settings for this filter, and it takes the type override, and if this is null and 1, it will return another object reference here that is a properly default configured settings object, right? And if this is non-null, and, if this is non-null and this is 0, then this is going to return the original reference, right? So this is just going to be piped down into here, right? So this is just a way to avoid a lot of even more boilerplate they would have to write in every single function, right? It's a little helper function, right? So it takes the nil is okay argument, and okay, nil is okay, right? I'm just saying that this settings argument, it's okay for it to be null, because that's kind of exceptional in the case of when I write code. What else? I feel like I'm over-explaining this. We're like 19 minutes in, and it's like a function that does nothing. Okay, so what about this? What are we doing here? So we have the input general arguments, and we're spitting out the general arguments. Why are we doing this? Shouldn't we just be done here? Because this can never be null. Why do we have this wrapper function here? Well, I'm pretty sure that this one is just a error check. Because we are going to do a little bit of inheritance and crazy void pointer stuff. And so there is the possibility that this thing coming in here might be the wrong object reference. I'm actually not sure what this does. Because I'm seeing this, I see this 1. I know this 1 corresponds to this number here. I'm actually not sure. You know what? I'm going to be full of shit here. Let's go look at this one. Let's go look at this gen type. So it takes gen and it takes type, right? So gen and it's type 1, right? And then it spits out gen here. Okay, let's go look at that. Let's go look at what it's actually doing, because I'm not sure anymore. So is it necessary? Am I just over-engineering? I'm over-engineering stuff, but... okay, so let's see what this says. Okay, so we have the general arguments object, and then we are declaring the type of that general arguments object. And if that general arguments object is null, we are throwing an error. Yeah, we're throwing an error, and we're also filter error code. Okay, and this is not, we need to format that a little better. Okay, so you might notice that when I do like a printf, I have like these square braces around stuff. That's just so that when I look at the code and I see this message in my logs, I know this is a hard-coded string somewhere in my code, and I know that this is a hard-coded string in my code. So anyways, now that I'm looking at this, we could do some extra error checking in here as well, to just make sure that this number is embedded into this type, to make sure that this type is actually what we think it is, because we are going to do some really dangerous void pointer code in our code. But right now, this actually does serve a purpose. This index is basically going to be used as an error code. So like if I see error code 1, right, if I see error code 1, then I know that this function right here was called from filter number 1, and filter number 1 was supplied a null configuration object for the general settings, right? And then if I call this from filter number 2, I should be calling this with a 2, and then if we crash, we get a 2 here. So this is kind of like a little bit of a hackish poor man's debugging, if you will. All right, so let's go back to where we were, right? So when we look at filter number 1 here, we see that we're calling that function with a 1 here. So if we crash, we see a 1. And then if we see filter number 2 right here, our inverter filter, we see that this argument right here is called with a 2. And then if we see filter number 3 right here, filter number 3 is unknown because we haven't gotten to this yet. We see that we're calling it with a 3, right? Okay, so that makes sense. So it's just a little error check inputs function, right? So I'm kind of paranoid. I'm a very defensive coder, so I never trust myself to write code correctly. So we want to error check these inputs. We want to error check this input with this function. We want to, this function not only does error checking, but it also gives us a default object if this reference is null, right? Because there's invalid combinations, right? If this is null, this has to be 1 for this function here, right? And if this is non-null, this has to be 0, right? And so if you supply these two parameters in an invalid combination, this function here is actually going to throw an error. Now, actually, let's go look at this function, right? Let's go look at this function and see what it's doing here. So right here, okay, so it takes a void pointer, right? So here's the thing, right? We know that this is a settings object, but every single filter takes a different settings object, right? So that means that if we're going to make a helper function, and it's the same helper function that gets called in every single filter function, and the first parameter that this helper function gets called with is the specific configuration object, well, that object is always a different object for every single filter, so we have to use a void pointer here. And therefore, if we also pass in this uint32 that identifies what the type of this is, we can actually grab what we need to grab, right? So remember what I said. When null comes into here, we supply a positive value, and that positive value identifies the default struct that we want to spit out. And if we pass in non-null here, then we just spit it right back out because we don't need to default configure it. Okay, so let's look at this. So function belonging to image 2024, it takes a knock, which is right here. It takes a type, which is right here. I underscore for input, void pointer, uint32, spits out a void pointer. All right, so O knock right here stands for output, nil is okay object. And if our input object is null and 0 is equal to the type number, then, oh, sorry, not null. I said that totally backwards. If the input object is non-null and the type is 0, we're just going to take the input and assign it to the output, and we're done. We're just piping it forward. All right, if the input object is null, right, so equal to 0, and the type is not equal to 0, then what we're going to do is we're going to use that input type to look up the default configured object for this configuration setting object, and then we're going to spit it out right here, knock. Okay, what do we got here? So we have some invalid configurations, right? If the input object is null and type is 0, that's bad, right? If both of these are 0, that's an invalid combination, right? They're both nil. Well, this isn't really nil because it's just an uint32. So maybe this isn't the best error message, but whatever. Okay, so if they both kind of like exist, you could say, that's a problem. And if they both don't exist, that's also a problem, right? So if this is null and this is 0, that's also an invalid combination. So both nil or both has. Both exist or both exist or both don't exist. Both of those are invalid combinations. Once again, my error messages are in strings that have square braces around them, so that when I see this in the terminal, I know that it's a hard-coded string somewhere in my source code, and I can find it. ERR is a macro for an error function that I wrote in the code, and here we are returning output knock right here. Okay, so if we want to look at the, we're already kind of almost at 30 minutes here. But yeah, let's go look at this. So function belonging to image 2024 library, default, and it takes type, and it's going to spit out knock, right? So type is going in, and knock is going out, and knock stands for nil is okay object, and it's a specific configuration object here. Let's go grab onto that and see how it works. All right, so here is our function right here. It takes a type that identifies the specific configuration object for whatever filter we're using. We have our output knock object right here, which is void. We have our any object right here, which is also void. And I believe that these are both going to be pointers to the exact same object, but one is kind of like a wildcard cast, a void pointer cast, and this is kind of like a polymorphic cast. Remember how we talked about the any pointer that is kind of like a more restrained void pointer that allows us to do some polymorphism? That's what this line on 1416 is for. All right, let's go look at what we have here. So if the input type is greater than or equal to 1, because all filters are 1 index, right? The first filter is the nothing filter, and it starts at filter index 1, right? So if the type is greater than or equal to 1, and the type is less than or equal to the type maximum, right? So we have 3 different filters, then input type can be 1, 2, or 3, right? Okay, so if we have a valid type index, then we're going to do some logic here. And if we don't have a valid type index, we're going to say type index not recognized. All right, let's look here. So knock is the output configuration object, and we're using a lookup table here. So L underscores for lookup table is a lookup table that belongs to the image 2024 library, and it is a lookup table of default configured specific configuration objects for different filter types. So we put the filter type in, the input type, and we get out our configuration object. So you see how we're doing this call twice in a row? I specifically did it twice in a row like this, so it's more obvious that this object and this object are the same, right? We could have done it like this, where we make this, and then we could say that any equals knock, instead of just look this up twice. But I figured that writing these 2 lines of code like this make it more obvious what I'm doing, and it makes it more obvious that what I'm doing is intentional. So this is a void pointer, whereas this is an any type. And while it's casted to an any type, we can grab those first 2 parameters off of the object, right? So this is so every one of these objects in this array, right, is a different object. But their first 2 parameters is always the type uint32 and the is initialized uint32. So if we take any specific configuration object and we just cast it to an any type, and we just cast it to an any type, we can do this kind of polymorphic magic here, right? We can basically say that all specific settings types in our C code base extend from this any type right here. So any member ini, if it equals 0, then the object hasn't been initialized yet. What we're doing right here is lazy initialization, right? So we're going to get the object, and then we're going to see if it's initialized with the default settings yet. And if it hasn't yet been initialized, we will use this helper function here to populate this settings object with the default settings for that setting object. So the type, we're going to assign the type of this settings object to the input type. And we know that should be correct because here's the input type going in here, and we looked up in a lookup table, and all the individual types should be in the correct position within these lookup tables. For initialize, it just needs to be a non-zero value. I'm just going to put the max uint32 value right here, right? FF, right? 8 Fs in a row. R, G, B, and A bytes for a 32-bit pixel. Okay, so right here is the configuration object. Well, I'm going to go take a look at this. So let's go grab onto this. And function belonging to image 2024, default configuration any. We have our any pointer again, and input any. So once again, this is not really an any type. We have kind of like downcasted this to the conceptual base class, right? Because the first two member variables of every single configuration struct basically have the structure of the any type. So why we're doing this here is because instead of using just void pointers all over the place, if we do some of this, we get a little bit of type safety, right? Okay, so what do we got here? So first of all, we see the type. We're going to grab the type that we put into the object before we called this function. Input any.member variable type, and that type should be between 1 and the type maximum inclusive. And if it is in this valid range, that's good. That's good. Don't do anything. Otherwise, error invalid type cannot configure, right? So if we take this object, if we take this struct reference, and somehow when we try to grab the number off of it, it doesn't give us, you know, the number in this range, then that could mean that we did something bad with, you know, all of this kind of loosey-goosey void pointer craziness that we're doing, right? Okay, so if everything is actually okay, right? If everything's okay, we're not going to crash. And if we don't crash, we'll get down to this code down here. Now, this code right here is kind of complicated, so I decided that we would just write it twice. So we have a configuration variable right here. Data belonging to image 2024, use vtables. So here's the thing. I don't use switch statements in my code, because if you want optimized code, then you should be using a vtable, like a jump table, like a lookup table. And if you want code that's like just easy to read, then just do a big if-else, right? Like, I don't think a switch statement is good because it just seems like a half-assed compromise. Like, if we want the optimization, let's go all the fucking way with a lookup table. Yes, very fucking hard to read code. Or we can go the other way, and we can write this very, very stupid-ass code, but it's very easy to understand. But it's not as optimized because, like, every single one of these conditions has to be evaluated, right? And the longer this block of code gets as we add more and more filters, the more and more time it's going to take for this branch of code to execute. Whereas this branch of code, no matter how many filters we add to this branch of code always takes the same time to make its decision. Whereas as we add more and more filters to this branch of code takes longer and longer to make its decision on what default configuration function it needs to call. All right, so why don't we, so basically what I'm saying here is that this code here and this code here do the exact same thing, right? And the reason I'm writing it this way is because this is confusing as fuck. So I'm saying, you know, if we're using the optimized vtable method, do this, and if we're not, do this. That way you can kind of look at this and say, what the fuck does this do? Oh, it does whatever this does, right? So why don't we look at the easiest thing first, right? So uint32t for type, and then any pointer a for the input any type, okay? And what are we doing here? Well, this is just a shorthand reference, T and A. So if the type is 0, 1, 2, or 3 respectively, then we call the default configuration for the any object for filter 0, 1, 2, or 3 respectively. So we're going to pass this pointer in, and we're going to configure it, right? So this is settings object for filter 0, settings object for filter 1, settings object for filter 2, and settings object for filter 3. Remember, even though all of these say that they're the same type right here, they're not actually the same type, but they're all kind of like conceptually the same base class, and so conceptually all four of these types extend from the any class, you could say. Why don't we go look at default configuration any 0 for a second. Well, that one might be a kind of whatever. I guess we're looking at all the code, aren't we? So default configuration any is the configuration object for the me crash filter. And the me crash filter is filter number 0. Filter number 0 should never be called, and if you accidentally call it, it will crash the system. And so this is, I believe, called offensive coding, right? There's defensive coding, and then there's like ultra defensive style of coding called offensive coding, and I believe this would constitute offensive coding, right? I have this whole function that its whole purpose is to never call it, right? And if you call it, it says that you screwed up because you shouldn't be calling default configuration for filter 0, because filter 0 is the air filter, and if you call the air filter, the filter engine crashes, the filter program crashes. Now, default configuration for the any object for filter number 1 is right here. Remember, this is not actually an any object. It is a derived type from the any type. And we don't have any configuration that we need to do for this, right? The filter number 1 was the do nothing filter. It does nothing, right? It doesn't really need any configuration. So we're not really doing anything here. We're just writing this here to make sure the compiler doesn't complain that we have an unused parameter. Now, any2 is our inversion filter, and we're not really doing anything here. I mean, there's some weird configuration we could add to an inversion filter if we really wanted to. Maybe we'll do that in the future, right? And then any3 is our unknown filter type because we haven't figured it out. And we'll do the configuration code here, right? So we have these different configurators that execute on these different objects. So remember that even though these say that they're all the same type, this is actually specific configuration type 1. This right here is specific configuration type 2, and this is specific configuration type 3 right here. And so once we get into these functions right down here and we have to actually configure things, what we're going to do is we are going to promote this type to the actual type that it really is, right? And in order to do that, I believe we have to take this and we have to cast a void pointer, downcast it all the way, and then upcast it to configuration type 3. Okay. So let's try to go back to where we were. Let's go back to the function. This is almost going to be an hour here. So we have this vtable section right here. Why don't we look at this? Function. This is a function type belonging to the image 2024 library. Default configuration function for an any type, which is an any filter specific configuration type. And then this is for pointer. So I don't make function pointer types, I make function types because I think it's easier to read. Let's go grab onto this and look at where it's actually declared for a second. So here we go. Type def void, and then function belonging to the image 2024 library, default configuration any. It takes a any pointer and it does something with it. It configures it, right? We have this right here, which is basically a type for void pointers to functions. So when you have really strict compilation on, data pointers and function pointers are not actually allowed to be mixed. So if you want to do kind of like void pointer logic with function pointers, you actually need to use like a generic function pointer, right? So this right here is the equivalent of a void pointer for a function, is what we're looking at right here. And then right here, what is this thing? Function image 2024, general, void, and type. So remember how we talked about every single filter function takes 3 arguments, right? It takes the general arguments that all filters take. It takes specific arguments that are specific to that filter. And then it takes a uint32 telling us which filter function we're calling. And this right here is not the actual prototype, not the actual signature of our filter functions. It is a it's a down-resed, more generic function pointer that can work on every single filter function, right? So instead of taking general arguments, one of the specific arguments for one of our specific filter functions, and then a type enumeration, we're putting void in the middle, right? So general settings object, a void pointer that's going to be casted to one of our specific configuration objects for whatever filter we're actually calling, and then a uint32 that helps us figure out what this void pointer actually is. So why are we doing this right here? Well, it's because if we want a array of filter functions, right? If we have 50 different filter functions, we want to shove them all into an array so that we can kind of pragmatically access them with some type of enumeration. If we want to do that, we need some type of common function type, and this is the best common function type that I could think of. What else? I don't know where I'm going with this. There's so much stuff in here. We're almost at an hour. I don't even know if I'm allowed to upload something this long. So right here, we have another V table here. What is this right here? Well, let's see. This is filter function. This is filter function 0, filter function 1, filter function 2, filter function 3, right? And we want to take all these filter functions and put them in one array, but there's a problem. And the problem is that all these filter functions have slightly different signatures, slightly different prototypes. So they're actually called prototypes, but I like to call them signatures, but I guess calling it a function signature isn't quite correct. If I say function signature, I just mean like the actual parameter types that are given to the parameter list and the return type of the function, right? But that, I guess, technically that's actually called a prototype, but using the word prototype always fucking confuses me, because, like, I think of when I think prototype, I think JavaScript. When I think of, like, the actual parameters given to a function, I think signature. So, forgive me if I'm using terminology wrong here. So, if we want to take all these functions, that takes a different middle parameter, right? The first parameter is always the same type. The middle parameter is specific settings specific to whatever filter index we're on. And then the third parameter is always a uint32 that identifies what filter function we're in, right? So we're going to have to take this, and we're going to have to take the address of these functions. We're going to have to downcast it to our kind of void pointer function pointer, our any function pointer right here, which is just an alias for a function image 2024 anyfunc, right? Any fn for anyfunc. And then once we've downcasted, we can re-promote it to something more specific, but not as specific as this. A specific function pointer type that all of these kind of can be... We want a function pointer that is as specific as we can be for the grouping of functions we have. That's what we're trying to do here. So GVP here stands for general, void, and type, right? G, V, and T. So this is the actual type right here, the actual function pointer, sorry, this is the actual function type right here. And this is also the actual function type here. And these are just like macros to make these lines of code a little bit shorter, right? So V right here is for vtable. So anytime you see an identifier with a V underscore, that stands for vtable. And the next parameter after the kind of the general category specifier is the library we're in. The library we're in is the image 2024 library. And this lookup table is going to be used by a subname space called easypng. And that subname space is just a way to get us like off the ground as quickly as possible and just get results as soon as possible. Because we're actually making a very ambitious kind of filter system here. but we want to be able to use our filters right now just to make sure that everything we have so far works. And this vtable here is part of that process. What else do we have? Oh my god, this is so freaking complicated, isn't it? There's a lot of other stuff, but, you know, maybe what we should get into is how the... There is so much craziness going on here. So we have easy PNG decks. Remember how I talked about, you know, we might want to shove all these different functions into an array and then access them by index? That's what this function does. Function belonging to image 2024. Sorry, I started there. Function belonging to image 2024 library. Easy PNG subnamespace. Index. It takes the uint32. I underscore for input. Dex is the index. Dex and dex, that lines up so that we know that we're calling this correctly. GVP was the general void and... why are we calling it GVP? Did I fuck that up? I did fuck that up. So that should actually be GVT, right? General, void, and T for type. I don't know why I, like, ended up... okay, so here's what we're gonna do. We are already taking forever for this. So I guess we're just gonna go 100% and hope that... we might have to, like, verify this YouTube channel now. I don't know if this channel is even verified. But I'm gonna show you what we do when we make a mistake like this, right? So we're gonna go up here, and we have a section. So we have this, like, index very close to the top, right? And I don't know... We'll figure out how we want to organize this, but I have an index that's not quite at the top, but this index tells us where everything else is, right? So the index actually tells us where the index is relative to the other sections, and one of these sections is the monk section for monkey wrench macros. Now, if we go to monkey wrench macros, we see a whole bunch of defines that have identifiers and square brackets like this. And what these defines are meant to do is they are meant to crash compilation if we use them. So whenever we have a misspelling of something or we want to refactor, we can turn the identifier into like a proverbial monkey wrench, right? So GVP, I've decided, isn't the actual identifier name. So I'm going to write GVP, and then right here I'm going to write use GVT, right? General void and type, right? So it stands for general, void, and type. And let's kind of go align that a little bit better, right? So, because I've made this little monkey wrench macro here, I'm going to show you how that kind of works, right? Let's go look at our console here. And let's zoom in here. And let's clear the console. And we're going to run our build script again. If my goddamn console doesn't fucking crash on me. Like, what are you doing? You weren't doing anything the whole goddamn time, and now you're like, just fucking, there we go. So let's do ./image2024.sh. So I named my build script with the exact same name as my C file, but a .sh rather than a, I believe a .c11 is what I used on this file. Yeah, .c11 right there. Let's go run that. Okay, so we run that, and we see error GVP redefined, so that's a problem. And then, so we already have a monkey wrench macro, not the monkey wrench that I thought we were going to have. But let's go fix that one problem here, right? So we see this is the place where we had previously defined it, or maybe not, whatever. Let's go fix it, though. So let's go find, okay, so let's go find this right here. So we know we don't want to actually use GVP, right? We actually want this to be GVT, right? We want that to be GVT, right? For general, G, void, and type. Okay, so we're gonna fix that. Now I see we're still using GVP here, right? So so we're not fixed yet, right? But let's see what happens, right? So when we run this again, we see unexpected identifier before blah blah, right? We caused a compilation problem. And then we see on line 109, define GVP, and then we have a little arrow here pointed to the square bracket, and it says use GVT general void type. So what I'm doing here is I made this so that, sometimes you make a mistake in your code and you get these weird-ass error messages that don't actually tell you the real problem. Well, this error message actually tells me the real problem, right? So instead of looking at what the compiler is telling me, I look at this little message right here that I wrote for myself that basically says, this is the wrong identifier, it's not GVP, you want to use GVT, which stands for General Void Type, right? So why don't we go fix that right now? So now that we have that, and we know that this needs to be GVT, right? We can go around here, and we can change this all to GVNT, right? GVT. Now, the cool thing here is that if we, for some reason, didn't do a full refactor, right? So let's say we accidentally did not fully refactor this. We missed something somewhere, right? Well, if we missed something somewhere, we're going to get this error message again that's going to point to where we're using that improper identifier again. All right, so now let's go /img2024.sh. Let's run our build script again and see if everything's running again. So we see some logs, forever alone compile. We're touching the file cat_1.png. We are saving cat1.png. We are exiting. Press enter to exit the program. Okay, so now if we go look at our folder here, the original image was cat0 here, and now we have cat1.png, right? They're identical because the filter doesn't actually do anything to them, but now you've seen how that kind of works, right? Okay, so I know that we haven't really gotten into the actual filter logic, though it is a do-nothing filter. But I think it is about time that we look at that do-nothing filter. Okay, actually, we still have a little bit of more structure here. So I didn't want to have to do this. I don't know if this is the best way to do this, but there's kind of we have vtables, but then we also have these wrappers. I don't know how I feel about this, but, first you have to actually solve the problem, and, a more elegant solution really happens after you've solved a problem multiple times. Now, if you notice that I'm doing a lot of craziness in this code, so I've probably written code like this before, but I guess I still haven't stumbled upon the most elegant solution, right? This doesn't feel very elegant to me. But basically, we can see that what this is, the easy PNG subnamespace of image 2024, it literally means easy PNG, right? Easy PNG file. And the idea of easy PNG is that a lot of this code is really fucking complicated. What if I just want to call a fucking filter and not, worry about all this craziness, right? Well, then I can use the easy PNG filter functions, right? If I want to use filter 1, easy PNG 1, right? I want to use filter number 2, easy PNG 2. I want to use filter number 3, easy PNG 3. I don't even have to supply any arguments to it. All right? So you can see that easy PNG 1 calls this lookup function, easy PNG dex, with 1 to look up filter number 1 and execute it, right? Easy PNG 2 uses this easy PNG dex function with 2 to look up the correct filter function and execute it, right? Easy PNG 3 uses a 3 in this function to find the correct function and execute it, right? So remember, easy PNG dex is right up here, right? And it uses this vtable of different filter functions. And this is actually a little bit of debug code that I need to get rid of, right? So right here, what we're doing is that if 2 was the index, then what we're doing here is we're making sure this GVT that we got out of the lookup table here is the same memory address as filter function number 2, right? Because even though GVT and this are, they look like two different types, right? Because GVT is kind of like a more generic function pointer type, and this is a very specific function right here. They actually should be the exact same memory address, right? So I'm taking this function number 2, filter function number 2, and I'm taking GVT that we got out of this kind of generic vtable, and I'm just making sure that they're the same memory address, and if they're not, I'm throwing this error that stands for you don't know jack about function pointers. That's what that stands for. Now, I don't think I actually wrote an explanation for that, and I feel like, a year from now, I'm not going to know what the fuck that means. So we might want to, like, put an explanation for this. Now, if a token has, like, dollar signs around it or hashtags around it, it's guaranteed to have an explanation at the bottom of the file. However, if a token just has underscores around it, there may or may not be an explanation for it. There's not a guarantee. So if I feel like adding an explanation, I will, but there's no guarantee, right? So let's make an explanation around. So you don't know jack about function pointers. Oh my god, that's very long. Let's just say func, because I'm sure I'm smart enough to remember what that stands for, right? So Y, D, K, J, A, F, and P. Also, you might have noticed that I put @ symbols around this, and that's what I do sometimes is, like, if I don't know what an identifier means, usually I can put @ symbols around the identifier and Control F for it, and if there's a definition, it'll take me straight to the definition. Okay, so let's go grab on to you don't know jack about function pointers, go back to where we were. So this function right here takes the index identifying a filter function. It uses the vtable to get the correct filter function, some miscellaneous error checking, and then right here is our filter function with the 3 parameters that all filter functions take. It takes the general arguments, it takes specific arguments, which are void here, and then it takes a index, which identifies the filter function, and that index only identifies the filter function if this is void, right? And so this, with the way we're calling this, we're saying call the function with the default settings, right? If this is 0 and this is a non-zero value identifying the filter number, then what we're saying is that we want to grab a default configuration settings object for the filter we're executing, and we're also going to call that filter with these general configurations. Now, what are these general configurations? Well, you might have noticed that with the easy PNG namespace, we are not actually specifying like the image size or whatnot. So what the easy PNG namespace does is when you load a file, it will always resize that file to exactly 512 by 512, and it will put those pixels in a static allocation of memory that doesn't have to be mallocked or freed. And the reason for that is just it makes it very simple to get up and running, because malloc and free can be very error prone, and by just saying, oh, we have a static allocation of 512 by 512 pixels, and for all these easy PNG functions, you can only use an exact 512 by 512 image. It just makes things easier, right? So it's kind of like this default simplified workspace for just getting stuff working, and the easy PNG namespace will always be for that. And if we want to do more complicated things, we have to use a different sub namespace that is not easy PNG or just something that's not easy PNG, right? So D is for data, image 2024 is the library that this code is in, and easy PNG is the sub namespace, and gen stands for general arguments. Now, if we go grab onto this, we can see what's going on there. So right here, we are in the data section of the system, and we see general arguments struct. It's not a pointer, right? It's not a pointer. We're actually allocating its memory right here statically. And data belonging to image 2024, easy PNG, the sub namespace, general arguments, and we are initializing it in line like this. Fuck, I forgot the name of this. There's a name for what we're doing here. I forgot what it's called though, right? But you can see that we're looking at each member variable and we are initializing it. And because we're kind of like statically initializing this memory, I believe everything has to be a constant reference. So you can't like have a function call here that grabs this number or a function call here that grabs this number. It all has to be like constant expressions, right? So the type of this general configuration object, the type number is 0, and There is no filter type 0, right? So the general argument type shouldn't really conflict with the filter types, or at least valid filter types, right? Because there is the me crash filter, which is filter type 0, but you should never call that. Is this object initialized? Yes, it is actually initialized, right? Because we're not 0 initializing this, we're actually initializing it right here, right? So it is initialized. The pixel array is going to be the memory address of this static array of pixels right up here, right? So byte, uint8, a byte. Data belonging to image 2024, easy PNG pixels. It's 512 by 512 pixels. There are 4 bytes per pixel. We're going to 0 initialize that memory right here. Okay, so I think there's this thing called like pointer decay or something. I forget why, but you can't just directly assign this to this. It just does not work. So you have to dereference the first element of the array and then take its address again, which looks like you're doing absolutely nothing. But I believe what you're trying to do is you're trying to decay the array into a more generic, like, memory address pointer. I don't know exact terminology, but I know you have to do this, right? I've written a little bit of OpenCL code and a little bit of Vulkan, and they both do this kind of thing in different places. I think OpenGL does as well. All right, so constant image 2024 easy width is going to be 512, and constant image 2024 easy PNG, oh, that should be height. That's a little bug. So it's a 512 by 512 image, so that's why I didn't run into any problems, but that's wrong. So you might notice here that we have these defines here. The width and height is not data, right? The width and height is not configurable, so it doesn't get a D underscore, it gets a C underscore, but C underscore is in a different section of the code base for constants, right? So since we're in the data section, everything here should start with a D underscore, right? Right, so D underscore, image 2024, configuration objects 0, 1, 2, and 3, right? And then down here is our static allocation of 512 by 512 pixels. And for our kind of easy PNG system, we just want to always apply the image filter to the entire image. So the X minimum left edge is 0 inclusive. The X maximum right edge is 512 minus 1 inclusive. The Y minimum top edge is 0 inclusive. The Y maximum bottom edge is 512 minus 1 inclusive, right? If it's a 512 by 512 image, then we address the pixels starting at 0. 0 to 512 minus 1 is all 512 addresses. 0 to 512 minus 1 is all 512 addresses, right? So this is going to go through this selects every single pixel in our 512 by 512 image here, right? So this general arguments object is going to be used with the easy PNG namespace for every single filter that we call. So are we ready to actually get to the actual function? Let's go down to the forever alone compile, right? So what is this? Why is there an if-def around it? What I'm doing here is when I make kind of like large projects with a lot of different subsystems, I try to make it so that you can compile any one subsystem all by itself, and it will give you some demonstration of how that subsystem works. That way, you have kind of this kind of self-documenting system where you can try to get your hands dirty and kind of work with the code to figure out what different subsystems do. Also, you know, C code, you can really easily just shoot yourself in the foot and do really horrible things like memory stomping and seg faulting, and sometimes that stuff can be really hard to debug. And by being able to compile individual modules of your project as standalone executables, it can help you kind of subdivide the code and figure out where the unintentionally malicious code in your code base is, right? So this image 2024 library is only for image filters. I eventually want to make a project that has like a graphical user interface. and renders the image with like OpenGL so that we can make an actual editor rather than just executing filters from the command line. So I don't know where I was going with that. Let's just look at this, right? So int main void and printf, we print the file that it's coming from, forever alone compile. And then right before we exit, we also printf the file it's coming from. We are now exiting, right? And so you probably saw that here, right? So forever alone compile, we're now exiting, and then some other logging messages telling us kind of what we're up to, right? These aren't the best logging messages. They're obviously kind of, I don't know, borderline schizophrenic in the way I write things, but basically we are touching file cat1.png to create it, because we can't really write to the file until it already exists. So touch file is basically like the touch operator in, or not the touch operator, but the touch function in Linux, right? Touch basically just makes sure that a file exists. If the file doesn't exist, it creates it. And if the file does exist, I believe it just like opens it and closes it, or changes the file access timestamp on it or whatever. But anyways, we use this just to make sure that the file exists so that when we're trying to save to the file path exists, right? So our touch file command will also create the necessary directory structure if the file is nested into a whole bunch of subfolders or something. cat001.png is the modified version of the file. Okay, let's go back to the code. So function image 2024 ini for initialize, and then right here, we're going to use the PNG load command, but this is the easy PNG load, right? It belongs to the easy PNG sub namespace and PNG load, right? How do we load the PNG? Just supply it the path, to the relative path, right? Dot /, so dot for current folder, / cat0.png. Simple, 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 right? Now, obviously, there's more complicated ways that we could open files, but we just want to do it as simply as possible, right? We're not even saying where this goes, right? That's the whole point, right? Keep it as easy as possible. Because we have that static 512 by 512 allocation, we can just say, hey, open this file and just throw that in that static allocation that's 512 by 512 pixels, right? So if we open up this file and it's not exactly 512 by 512, our code is going to resize it to exactly 512 by 512, and then load it into that, copy it into that 512 by 512 buffer we were looking at earlier. We're going to then execute filter number 1, which is our do nothing filter, and then we're going to save the image back to the same relative folder, the current directory, but we're going to call it cat1 instead of cat0 here. And then we're now exiting, right? So we can verify that that's actually happening, because instead of taking my word for it, why don't we go delete cat1? Let's go just delete that. Yes, I want to delete that. Okay, so now it's missing. And we could just, you know, double click this, right? Why don't we just double click this? Because we already know, we've already seen it in the console. Why don't we just double click it for ease, right? So if we double click it, it popped open on another monitor. It's actually right over here. And I'm actually a little bit confused because is it segfaulting on us? What the fuck is happening here? Okay, so that doesn't look good. That doesn't look good. Well, everything worked, but that delay, I did not like that delay. Sometimes that happens. It's probably like what my hard disk probably had to spin up or something. That's my guess. Let's close it though, right? So you can see the forever alone compile. You can see this, you can see that, you can see that. And indeed, look, that image popped up again, right? So if we delete that, let's do it one more time in case you didn't see that, because I was kind of like all over the place there, right? So we just deleted cat1, we have cat0, right? And then, well, we can execute it this way this time. Actually, no, let's not do, well, I don't know, whatever. So pay attention right above this green bar right here, right? We see this many files here, right? There's going to be a new one that's going to pop up once we do image 2024.sh. Let's go run that. All right. So now you see there's a cat1.png. Okay, so we are an hour and 9 minutes in, and we haven't even gotten to the logic of our do nothing function, right? There's this whole framework that I've kind of been going over. Why don't we actually look at the do nothing function? Let's kind of trace backwards, right? So function image 2024 easy png1. Let's go grab onto that, go control F for it, see where it is. Okay, so easy png1 is a wrapper for this more generic function that calls different filter functions by using the filter index, right? So filter number 1, filter number 2, filter number 3. We want to look at filter number 1. So now we have to go into this png dex function. In our code, we never use forward declarations. So if I go control F on this, and I want to find where this is declared, all I have to do is search in a backwards direction and not wrap around. And the first reference to this should always be the declaration, because we do not do illegal forward declarations to function calls in this code base, because then it makes stuff just very easy to find, right? And indeed, the very first declaration highest up in the file is the actual function declaration that we're looking for. All right, and we already went over this. So all we want to do is kind of trace things back and figure out where it's being called from, right? So we see we have this vtable, right, of functions, right, that are being called right down here. And so why don't we go look at the vtable? So vtables and lookup tables can make your code very efficient and organized, but they also add a lot of indirection and confusion, right? This is very confusing. Look at all these steps we're jumping through just to find the actual fucking function that's being called, right? Now, why are we going through all these hoops, right? Isn't that supposed to be the easy code? Easy PNG? Yes, it is the easy code in terms of using it, right? But in terms of all the implementation is actually quite convoluted, right? If we're trying to do easy code in terms of like using the code, then we would just grab directly for this function rather than, you know, going through all these loops, right? Okay, so here is the actual function right here. Function belonging to the image 2024 library. Function number 1, the do nothing function. The general argument struct, the specific argument struct that only applies to this function, and a uint32 that should be 0 if this is non-null, and should be 1 if this is null, to allow us to fetch the correct default arguments object. We already went over these. Let's go over all of this logic right here, right? Okay, so first of all, what we're doing is we are declaring an int32 x, y, I, c, x0, x1, y0, y1. What's all that? Well, x is the x pixel position, y is the y pixel position, I is the one-dimensional index. So you can specify a pixel position by an xy or by a one-dimensional scanline index, I, right? So I is the one-dimensional representation of the pixel coordinate, and then xy is the two-dimensional representation of the same coordinate. And then this is a index coordinate, a scanline index coordinate for our pixel. So let's say we have a 10 by 10 image. Well, then this index is going to be 0 to 99, right? What about C? Well, C is the actual byte index of our pixel. So there are 4 bytes per pixel. So if this value here, I, let's say I goes from 1 to 99, 100 pixels. Well, C would go, did I say 1 to 99? 0 to 99 for 100 pixels. If this is going 0 to 99 for 100 pixels, this would go 0 to 399 for 400 bytes, because there's 4 bytes per pixel, right? So 0 to 399 makes 400 unique addresses. So the C address here is just I times 4. Okay, x0 is the left edge, x1 is the right edge, y0 is the top edge, and y1 is the bottom edge. And this is all inclusive boundaries. So these variables are going to be derived from our different configuration structs. Actually, this is all from the general settings struct. We're going to unpack the general settings struct here. Now, you notice that all these lines of code are marked boil for boilerplate because every single function is basically going to have the same kind of prelude and the same next xy at the bottom, right? The stuff right here is the stuff that's going to be different for different filter functions. Okay, so with that said, what else do we have? We have the width and the height, and we're not actually using the height, but I kept this line here because in future filter functions, we might actually need this. Now, why do we need the width in every single filter function? Well, it's because the formula to go from xy to index always needs to know the stride of the image, like how many pixels are there per row, and that would be the width parameter, right? So we're taking the general argument struct and grabbing the width and assigning it a w, general argument struct, grabbing the height member variable, assigning it to h. And then taking the, I guess we're being kind of inconsistent here, right? Because we used all these underscore variables, and all of a sudden this is just called pix instead of with a p with the underscore. But I don't know, this just feels the most readable to me. My style is weird, I don't know what to tell you. So member variable pixels for our pixel array, which is an array of unsigned 8-bit integers, right? So this is a pointer to an array of memory. So pix equals member variable pix. And then when we evaluate our loop here, if we want to do our loop as efficiently as possible, we don't want to have to look up the memory addresses every single time, right? So this is just an optimization for this loop here, right? And we're writing C code, so we might as write it as optimized as possible within reason. So we're going to unpack the member variable x minimum left edge, assign it to x0. We're going to unpack the member variable x maximum right edge, assign it to x1. We're going to unpack member variable y0 top edge, assign it to y0. We're going to take member variable y1 bottom edge, and we're going to assign it to y1. These more terse variables with less redundancy in them. And then we have our loop right here. Now, if you're wondering why the y is on the outside and the x is on the inside, because you're thinking xy makes more sense than yx, well, you're wrong in this case, because we want to go in scanline order, right? And in order to go in scanline order, we have to go to the next row, every single pixel in that row. Go to the next row, every single pixel in that row. Now, if we really want to do this the most efficiently, we wouldn't even do this, right? We would directly go for the pixel index and convert that to the base address of the pixel. Because for this specific filter, we do not actually need knowledge of where the pixel itself is positioned in the larger image. We don't actually need this information. So we could just directly go for this, right? But this do nothing filter, the whole purpose of the do nothing filter is just to be an example of how we need to write other filters, more complex filters for the engine. So even though there are optimizations we could do this code to make it more efficient, the do nothing filter is basically a template to show you how we need to write other filters in the future, right? So we're going through the XY pixel coordinate in scanline order. Then we're using this formula right here to convert the XY position to an index. So the Y address of our pixel array basically tells us how many filled rows of pixels we have, right? If Y is 0, we have 0 filled rows of pixels. If Y equals 1, we have 1 filled row of pixels, right? So we take the number of filled rows of pixels, we multiply it by how many number of filled pixels there are per row, the width in pixels of the image, and this multiplication right here, the y-axis number times the width, this gives us the base address of the current row of pixels we're on. Then we can add the remainder x to seek into the base address of that row of pixels. And this formula gives us basically the one-dimensional scanline index representation of this xy pixel coordinate. There are 4 bytes per pixel, right? So if we take this index right here and we multiply by 4 here, we get the component address. So I use C for component rather than B for byte because it's for component color, right? Now we could have called this R for red because we are using RGBA color, but that makes the code asymmetrical. I do not like asymmetrical code. If you notice how OCD my code is, I don't like asymmetry. I like everything lined up and symmetrical. So right here, from the base address of our pixel, which is red, if we offset by 0, we're still on red. We have red, right? And then it's RGBA, right? So RGBA 0, 1, 2, and 3, right? 4 bytes per pixel, right? The actual pixels of our memory are stored as a loose collection of bytes. Now, you might think that it would make more sense to have like one entry for one pixel and then just store the pixels as uint32s instead of uint8s. But I guess it is more optimized for graphics hardware to store your pixels as loose collections of bytes like this. So as you can see, we are getting the value of the 4 different bytes from our pixel array, and then we're just shoving it directly back into the same exact memory location, right? So these addresses here are identical to these addresses here, so we're actually doing absolutely nothing, doing nothing, but it is our do nothing filter, right? It's our do nothing filter just to show you kind of the workflow that we need to do here. Now, this video is for the do nothing filter. In the next video, we'll go over the inversion filter and the logic for the inversion filter, which is pretty simple. I mean, you can pretty much already understand it from right here. But this video here is this is going to be the longest video, right? Because I just wanted to explain like how the whole project is put together. Also, the bottom half of the file is commentary for the most part, right? And then the top of the file is code, right? We're trying to keep the code at the top of the file and then the commentary at the bottom of the file. And whenever you don't know what something does, sometimes there'll be explanations, right? So see how this kind of like section marker here has hashtags around it? The hashtags mean that if I control F onto this section marker, that it should bring me to a commentary section, right? So anytime we have like a block of code that's like really hard to understand for some reason, or I feel like that block of code needs more explanation, I will signify that there's extra information for that block of code or line of code by putting symbols around the comment section marker. Now, if you see dollar signs, the dollar signs mean that we're marking like a line of code, right? We're marking like one discrete area, right? I'm marking this line of code here. When you see hashtags, if you see hashtags somewhere, hashtags are marking like a section of code rather than like a line of code, right? So you see this right here as hashtags. It's marking a section of code. So if we grab onto this identifier and control F parkour, oh, it doesn't bring us anywhere. Oh, because this is our example section, because we're at the top of the documentation. So why don't we just grab onto this dollar sign, this pound underscore. So right here, we see a little bit of explanation. Let's grab onto this and see what code it's explaining, right? And so you can see that we have all this code right here, and we have a section marker that starts here, left justified, a section marker here that ends here, and because we see that there's hashtags around this section marker, we know that if this statement here doesn't make enough sense, we can grab onto that statement and get like a further explanation at the bottom of the file, right? And so these are the includes that we need for the FileBoy subsystem that I've embedded into this project. The FileBoy system is out of the scope of this project, but it's just a file input-output system that manages like saving and loading of the PNG files, and it also uses the UPNG, not UPNG. I use UPNG for JavaScript code, and then I use load PNG when I'm doing C code. So the FileBoy system under the hood wraps a lot of load PNG functions. Anyways, there is a lot of code that I haven't explained here. I've explained the most important parts. I've explained enough of this to where, like, you know, if I want to understand the basic idea of what this library does, you know, a year from now, I'm going to understand for myself. So, hopefully that kind of makes sense. It is kind of confusing. It's crazy. What I'm going to do eventually is, well, first of all, the code is open source for this image library. The image library is actually a subcomponent of a larger game engine that I am not open sourcing, but I'm going to give this to you. Now, eventually what I'm going to do is I will compile an executable. Like, once this project is further along, I'll compile an executable that will allow you to create configuration files to batch process images with a given combination of filters. So if you mess around with my code and you find like a combination of filters that does something like really cool to the image, and you want to just go through like a whole folder of images and apply that same filter to like every single image and create like a batch of cool images for like an image gallery, then you'll be able to do that with this code. All right, so this is forever. I'm gonna hope this is gonna be the longest video because I don't really like I don't actually like making these long videos because it takes up a lot of memory on my hard drive. So with that said, I'm gonna get out of here and let's go back to our opening screen, right? So this is the do nothing filter. That has been the end of the do nothing filter. You can find this code on GitLab. Go to, let me go look at the URL right now. What is the URL? Okay, let's go look at that URL again. Right, so the URL is gitlab.com/kanjicoder/img2024. That is for the image processing library. That is going to do a lot of bitmap filters, and it's all written in pure C code. So if that interests you, like and subscribe to my channel. My name is Kanji Coder, and I am making an image library to show you how to do low-level graphics.